So we're going to start section 3.1, summaries for symmetric distributions. Chapter 3 is going to focus on numerical summaries for center and spread. So whenever we're looking at a distribution, we're always going to be wanting to look at our shape of our distribution, where is our center, and what is our spread. So in chapter 2, we focused on ways to see the shape by using the correct graph given the data that we're working with. And so now today we're going to be talking about ways to give a quantitative measure for center and spread depending on the shape of the distribution. So a numerical distribution can often be summarized with two numbers, one to measure the center, and that'll be our first focus, and one to measure variability or spread, as we often talk about it. So there's several measures of center and spread that we're going to be learning about, and the best one to use depends on the shape of the distribution. And this is very important, so we're always going to need to look at our distribution using the appropriate graph to determine the shape, and then pick the correct measure of center and spread. So in the previous chapter, we just used just looking at our distribution to determine which was a typical value or where the center of the distribution is. Obviously, that would be somewhat subjective, and so today we're going to talk about how to quantify the center of a distribution. So the data set below contains 9 Boston Red Sox players from 2015. It's the age of the players. So the variable we're looking at is age, and our observational unit for this data set are Boston Red Sox players. So what is a typical age for the following Red Sox players? So let's go through and just first look at the graph and just kind of eyeball it. It looks like it could be like right here. We could say it's possibly 27, the typical age. Would everybody agree on this perfectly? Maybe, maybe not. So let's go and talk about how we can actually calculate a measure of center. So in order that everyone's going to arrive at the same answer, we are going to quantify this measure, and one measure of center is the mean. And so this is probably something that you've calculated before. The mean is the average, the arithmetic average of the distribution. So to calculate the mean, we are going to sum up all of the observations, so sum up all ages and divide by the number of observations. So in our case, that's 9. The formula for the mean, which didn't copy over that well, looks like this. So X bar is the symbol we use to talk about our sample mean. It's equal to the sum over all of our X's, so that the sigma, this symbol here just is saying sum. We're going to sum up all the X's and divide by n, which is the total number of observations. So let's go ahead and calculate that together. So we are going to find our mean. So we want to get used to using our symbol for mean, X bar. And then we're going to sum up all the ages. So we could just start at the top of the table and go down 31 plus 23 plus 22 and keep going till we get to the last observation, which is 28. And we're going to divide all of this by 9, the number of observations. So that comes out to be 243 divided by 9, which is equal to 27. So my ballpark looking happened to be right on in this case, and that's not always true. So 27 years is the average or the mean age of baseball players for this data set. So let's take a closer look at why the mean is thought of the balancing point of the distribution. So we are going to mark the mean on this graph here. So our mean was 27. So I'll put it right here. Here's our mean. And we want to find the distance of each player's age from the mean age. So we could start by looking at the ones that are above the mean. So this player here is a distance of 1 away. And this player here is a distance of 2 away. And then we have 2 players who are a distance of 4 away. And finally, our last one over here, I need a longer line, is a distance of 5 away. So those players all have ages that are greater than the mean. We can also look at the players who have ages less than the mean. So this player, the first one I'm looking at here, is a distance of 2 away, but it's negative. It's less than the mean. The next player I'm looking at here has a distance of 4 away, and the last two have a distance of 5. So if we include positive and negative signs, okay, so all of the red ones are less than the mean. We could say they're all negative. And of course, we have 2 players that are 5 away. So we wouldn't want to forget that we have 2 players there. And also we had 2 players here that were 4 away from the mean. So down here, we can notice that a negative deviation indicates that an age is less than the mean. A positive deviation indicates that the age is greater than the mean. So this were our green ones, and the negative deviations were our red writing up there. So if we sum up all the 9 deviations, what happens? Well, first let's sum up our red ones. So we had 2, -5, plus -5, plus -4, plus -2. That sums up to be -16. So the deviations that are less than the mean are -16. The deviations that are greater than the mean, we had 1 plus 2 plus 4 plus 4 plus 5. And that also comes to 16. So if we add up all the distances from the mean of each observation, they sum to 0. -16 plus +16 would be 0. And that's how we can always, this is always going to be true. And that is how the mean, you can think of it as the balancing point of the distribution. Okay, so now let's look what happens if we have one more data point added to our data set and see what happens to our mean. So notice that the new data point that we have added is this data point down here. The 10th player, Ortiz, is age 40. So right away, looking at our distribution here, we're seeing that data point. It's pretty far away. We might notice or talk about this being an unusual data point or an outlier. It's far away from the rest of our data set. And so now let's see what happens when we calculate our new mean. So our mean is going to be x bar, and it's going to be the sum of all of our data points, which we just summed those ones up already, and they were 243. So we don't need to resum those. But we also need to add our new data point, which was 40. So we have this additional age. And overall, that's going to be 10 ages now, 10 observations. So we're going to divide by 10. And our new average or mean is going to be 28.3 years. Okay, so our old mean, just put a little mark on here, was at 27. Now our new mean with our new data point is 28.3. So when we have a data point that's pretty far away from the rest of our data, the mean is going to get pulled in the direction of the outlier. Okay, so the mean is affected by outliers, and specifically, we have some language that we want to learn that your results show that the mean is considered to be not resistant outliers. It doesn't resist the pull. It gets pulled in the direction of an outlier. So the mean is not useful as a measure of center when you have skewed data or outliers in your data set. It is most useful, and this is important, that's why we're always going to look at our data set first, when your data is symmetric. So if you have symmetric data, then the correct type of center measure that you want to do will be your mean. That's when your data is symmetrical. Okay, so going on, we have the following distribution of ACT scores for a class at a junior college, and the mean score is 24.6. And that's put on the histogram for you. So this is from our textbooks. Do you think the 24.6 accurate represents a typical score for these students? So yes, I would say it does. The other thing I want to point out is that this is I guess it's a histogram, or actually think of it as a dot plot of these scores. And so this graph is the actual data. We could like kind of picture an idealized version of it with a nice smooth curve. It's mostly symmetric. And so yes, this does look like a good way to represent the typical score. And we might mention that the shape is symmetrical. Okay, so the following, we're going to look at another distribution. The following distribution contains salaries for professional baseball players from 2010, and the mean salary was 3.2 million. It's marked right here on our histogram, and now we want to say, okay, we're looking at this. Does that look like the typical, would you say that's a typical salary of a baseball player? That's probably not that great. It looks more like a typical salary of the baseball player might be less than 1 million or around 1 million, right? Probably closer to like 1 million we can put here. So the average or the mean, this is our X bar here, doesn't appear to be a good way to represent the typical salary. And what's happening is that our mean is being pulled in this direction. Like we've got some, first off, our shape of this distribution is skewed to the right, and we've got some really big the tail is pretty long, pulling our mean in that direction and not giving a good typical value to describe this data set. So this is skewed right. And so again, we're just emphasizing the idea that the mean is not a useful measure when we're talking about skewed data sets or if we have outliers. So the mean gives an accurate idea of a typical value in a symmetrical distribution. Okay, I've said this several times, so you can see this is a really important idea. Also note that typically you can use technology to calculate the mean. You should be able to calculate a mean for a small data set. You'll have to do that on a test, but in your homework on MyStatLab, you're often going to have big data sets. It's perfectly good to use StatCrunch to calculate the mean. It will always do it. And word of warning, it will do it even when it's not the appropriate measure of center. So you must always start with a picture to make a decision about which measure of center to use. So if you have symmetrical data, you're going to use the mean. In section 3.3, we're going to talk about another measure of center. That's the appropriate one to use when you're looking at a data set that's skewed. So for now, we've only covered the mean, but remember, you're always going to look at a picture. Okay, I'm going to look here at number 12. Is the mean enough to describe a situation? So just mentioning the typical value, is that enough to give a picture of what the distribution looks like? No, not usually. Actually, every time we describe a distribution, we want to describe the shape, center, and spread. So chapter 2, we did shape. We're starting to talk about center. And now we're going to look further into spread. So consider the following information concerning American women. The average height of American women is 5 feet 4 inches. The average height of an American female fashion model is 5 feet 11 inches. Are these two means enough to compare the distribution of American women to American female fashion models? Probably not. All we know is the typical value. So which of these two groups would you guess would have more variation? Likely the average American female. They said the mean is, 5 feet 4 inches, but there's going to be women that are shorter, women that are taller, and the spread for this is going to be pretty big, I would imagine. So likely we expect to see more variation there. Whereas the female fashion model, they said it was 5 feet 11. We're probably looking at a much smaller spread in the data, that more of the women are typically close to 5 feet 11. So that would be another key piece we're going to want to look at, is how spread out is the data? How far away are your observations from the mean? So the first type of spread is definitely the easiest type of spread to calculate. This is called the range, but it's not the most useful. So it's often given, but again, you have to be very careful when interpreting. So which group of American women do you think have a larger range? Probably our average American females would have a larger range. The range is calculated by literally looking at the difference between, oops, I meant to change color, the maximum value and the minimum value. So it's only looking at 2 data points to calculate it, which makes it nice and easy to calculate, but again, could be very misleading. If, just hypothetically, there was one fashion female model down there that had, that was much shorter than the rest of them, and we calculated the range here, the range for these two things might look completely the same, and yet the distribution shape looks very different. So we always have to be very careful when using the range as a measure of spread. So here's the warning. Although it's easy, it only relies on 2 data values and it's not very descriptive. So we need a better way to measure variability or spread. So one of the things we might be interested in is describing how far away is the typical value from the mean. And that is what we are going to look at next. So the following 2 histograms, also from your textbook, show the daily high temperatures in degrees in Fahrenheit for 1 year from Provo, and one of these is from San Francisco. So over here we have Provo, and this histogram is San Francisco. Describe the shape and center of these 2 distributions. So these are a little bit tough to describe. But so let's look at the shape of Provo. I wouldn't really say it's symmetrical. We've got these tall bars over here. Maybe we might even think that's not a very good sketch over, but maybe it might be bimodal. You definitely want to give some information that there seems to be 2 peaks, like one over in this area and one here, if you were describing the shape of this. But what would we say is a typical value? So we want to think of what we think the center is. And maybe that looks like it would be in this area, maybe around 65. It's hard to say, but that could be a good guess of it. Looking at San Francisco, if we were to describe the shape, again, you'll notice that shapes aren't always clear cut. Some people might think, oh, okay, this is kind of symmetrical. Others might say it's skewed a little to the right or skewed right. And the center, the typical value, I would say again, it's probably in this area around 65-ish, maybe 65 to 70, so somewhere in there. Now, which city has the greater range in temperatures? Provo goes from, looks like from 20 to, 110 maybe. 105, I guess. So let's see. I was using blue. So Provo, the range I said was 105, maybe to 25. We're just estimating. We don't have the actual max and min data points. And so the range in Provo is 80, and in San Francisco, it looks like it ranges from about 90 to 50. So the range is 40 degrees. So that does give kind of some information about these 2 distributions. But another measure of spread, and one that we're going to spend a lot of time working with, is called the standard deviation. A standard deviation is a numerical summary that measures the spread of the distribution by calculating the typical distance of the observations from their mean. So basically, we're going to look at all the observations and figure out the average distance each observation is from their mean. And which city above do you think will have the greatest standard deviation? Again, if we're looking at all the observations and their typical distance from their mean, then there's like Provo over here has a lot of observations that are pretty far away from the mean, where San Francisco has many that are really close to the mean. So Provo is going to have a greater standard deviation, Provo. Okay, so let's talk about the standard deviation. The formula for the standard deviation always looks slightly scary when people first see it, but it's really not as bad as it looks. And an important piece of information is that you have to have a good understanding of the standard deviation, but you are not going to have to calculate it. That means that on the homework, when it says find the standard deviation for these data sets, which it will, I want you to use StatCrunch to find the standard deviation. So the symbol for the standard deviation of a sample is S. And we're going to talk about this, but we're going to take the square root, so that's going to be there. So let's look at what's inside this square root. The first thing here in this parentheses is X, that's an observation, minus the mean. So we're looking at how far away is every observation from the mean. And we're summing that up. And we talked about if we sum that up, we've already tried this, if we sum up how far away every observation is from the mean, that would be 0. So we need to do something so we don't have these negative signs. And so what they've done is they square the distance each observation is from the mean, then sum it up and divide by n minus 1. So n is the sample size. So this is basically finding the average distance any observation is from the mean. And that's a good way to think about it. We are going to calculate it here once together. And then remember that in the future, you're going to use StatCrunch to calculate this. So I just want to go through the pieces so that you can understand what they all are. So calculate the mean age. I'm going to just give us that. That's 16. So here we have ages along here. That's the variable. I'm not sure actually what our observational unit is for this data set, but we have mean ages, or we have ages along here. And now we're going to calculate how far away each of the observed is from the mean. So 14 minus 16 equals -2. I'm not going to do this for every data set point. 15 minus 16 equals -1. All these 15s are -1. All the 16s, well, that is the mean, so they're 0 away. And we can keep on going down this table. 17s are 1 away, and they're positive. 18s are 2 away, and they're positive. 19s are 3 away. Is that it? Yeah, that gets us to the bottom. Okay, so that's our first column there. The next column we have is that we're going to square this distance. So we're going to square -2, and when we square a negative number, we get a positive number. So 4, 1, 1, 1, -1 squared is +1. 0 squared is 0. I'm just going to fill this in. So we have 0, 0, 0, 0. 1 squared is 1. 1 squared is 1. 1, 4, 4, 9. Okay, so we have just found all of the squares of the distances away from the mean. So what we need to do is sum all of this column. We're going to sum my red column, and that's this part of the formula. Okay, and so that comes out to be 40. And our 40, yeah, sorry, 40. Okay, next it says divide this by n minus 1, right? We're taking an average or about typical, so we want to divide by, usually by n We don't get into this in this class, why it's really n minus 1 in this case, but so 40 over 17 minus 1, and that comes out to be 2.5. And our right now we're working with, years squared as our units. The last piece of our formula says after you sum these distances that you've squared and divided by this, you're going to take the square root. So we're going to take the square root of 2.5, and that will give us 1.58 years. So we've already talked about why when you sum up this column here, the distance from the mean column, it is 0. Remember, that was the balancing point of the distribution is the mean. And so when you sum up all the observations distance from the mean, because you have the negative deviations and the positive deviations, the sum is 0. So the next little piece of information here is about the variance. That's just another measure of spread for statistics. We don't typically use it in here, but this is the variance is the standard deviation before you take the square root. And so that was at that point 2.5 years squared. So I just wanted you to hear it once, but we don't spend any more time on that in this class. You don't have to really worry about that. The last part of this section, we're just going to look at a histogram again. And so this is a histogram of our ages. It barely fits on here. We said that the average is 16. So those 16s are hidden in this tall bin there. And so, but we can think about, okay, it's about 1.6, the standard deviation. And so we're going to have some of our values be very close. They're going to be right on the mean or within one standard deviation away from the mean. And then some are going to be further away from the mean, more standard deviations away. So this is the measure that we most typically use for spread. And that wraps it up. So today we talked about a symmetrical distribution for shape, and that when we want to talk about center for symmetrical, we're going to use our mean, and when we talk about spread for a symmetrical distribution, we're going to talk about standard deviation.